this experiment, we investigated constant acceleration using a cart and hanging mass system. The purpose of the lab was to test Newton's second law, which states that the net force acting on a system is equal to mass times acceleration.
Now on to Mark with the breakdown.
For the theoretical model, we modeled the system assuming negligible friction and air resistance. The only unbalanced force causing motion was the weight of the hanging mass. Using Newton's second law, we derived the equation. Acceleration equals mass of the hanging weight times gravity, which was 9.8, and then we divided that by the mass of the hanging weight plus the mass of the hanging cart. Using a cart mass of 0.195 kilograms and a hanging mass of 0.015 kilograms, we calculated a theoretical acceleration of 0.70 meters over second squared.
With us, let's go to Omar with the acceleration explanation.
Position versus time graph. From the position versus time graph, we calculated acceleration by first determining two velocities from the slope of the graph, then using the acceleration formula. The acceleration formula is final velocity minus initial velocity over final time minus initial time. Our calculated acceleration from this method was 0.37 meters per second squared.
Let's see what Tesla has to say about theoretical acceleration.
From the velocity versus time graph, acceleration was determined as the slope of the line. Using two velocity values, we calculated an acceleration of 0.096 meters per second squared.
From the acceleration versus time graph, we selected the constant region and calculated the mean acceleration. This value was 0.05 meters over second squared. We compared each experimental acceleration to the theoretical value of 0.70 meters over second squared using the percent error formula, which is percent error equals theoretical minus experimental over theoretical times 100. So the percent errors were 47.1% from the position graph, 86.3% from the velocity graph, and 92.9% from the acceleration graph. These percent errors are significantly higher than the expected threshold of 10%. The likely causes include friction between the cart and track, pulley resistance, measurement noise from the motion sensor, and improper data point selection. In theory, all three graphs should produce similar acceleration values because they describe the same motion. However, experimental imperfections cause variation. The velocity versus time graph is generally considered the most reliable because acceleration is directly determined from the slope of a linear relationship.
To further understand this phenomenon, it is helpful to consider how changing certain variables would affect the outcome. If we increase the independent variable, for example, if we doubled the mass, we could expect the dependent variable to change according to the theoretical relationship described by the equation. If the relationship is linear, doubling the independent variable should approximately double the dependent variable. However, if the relationship is not as linear, the change would not be proportional and would follow the mathematical model more dramatically. Additionally, if friction or external forces were completely eliminated, we would expect our experimental results to more closely match theoretical predictions. This type of analysis helps confirm whether our data follows the expected model and demonstrates a deeper understanding of how the variables interact.
Although our experimental results did not fall within the 10% threshold, the experimental demonstrated the relationship between force, mass, acceleration, as described by Newton's second law. The discrepancies highlighted the importance of careful data selection and accounting for real-world forces such as friction.
In a real-life situation, this experiment is similar to two trucks connected by a heavy cable over a pulley system. Imagine one truck parked on a flat surface and the other hanging over the edge of a loading dock. When the hanging truck begins to fall due to gravity, it pulls the other truck horizontally. The acceleration of the system depends on the gravitational force acting on the hanging truck and the total mass of both trucks combined. According to Newton's second law, the greater the pulling force relative to the total mass, the greater the acceleration. This is directly analogous to our lab, where the hanging mass provided the force and the cart represented the horizontal object being pulled.
The following equipment was used in this experiment. We used the Pascal cart, which is the glider, track, hanging mass, string, pulley, motion sensor, balance scale, computer with capstone software, mass hanger, clamp or support stand.
So, to expand on the background a little bit, the experiment we conducted is based on Newton's second law of motion, first formulated by Sir Isaac Newton in 1687. This law describes the relationship between force, mass, and acceleration, and is mathematically expressed as F equals ma. In this equation, F represents the net force acting on an object, m represents the object's mass, and a represents its acceleration. The law states that the acceleration of an object is directly proportional to the net force applied and inversely proportional to its mass. This means that if the force increases while mass remains constant, the acceleration will increase proportionally. However, if the mass increases while the force stays the same, the acceleration will decrease. Newton's second law is a fundamental in classical mechanics because it allows us to predict how objects will move when forces act upon them. It applies to everyday situations such as pushing a shopping cart, driving a car, or, in some instances, launching a rocket. Engineers use this principle when designing vehicles, structures, and machinery to ensure they respond safely and predictable under different forces. By comparing our experimental acceleration values to the theoretical predictions from force equals ma, we can evaluate how closely our results follow this well-established physical law and determine the accuracy of our experimental setup. In this experiment, we investigated the relationship between force, mass, and acceleration using a cart and hanging mass system. The goal was to compare the theoretical acceleration predicted by Newton's second law with the acceleration calculated from our experimental data. Using the theoretical formula A equals mass Wg over mass W plus mc, we substituted the hanging mass 0.015 kilograms, the cart mass 0.195 kilograms, and gravitational acceleration 9.8 meters per second squared based on these values. The theoretical acceleration of this system was calculated to be 0.700 meters per second squared. This value assumes an ideal system with no friction, perfectly smooth motion, and no energy loss. Next, we used position and time data to determine velocities and calculate experimental acceleration. From our measurements, the initial velocity was found to be 0.0667 meters per second, and the final velocity was negative 0.40 meters per second squared. The negative sign indicates that the direction of motion was opposite to the chosen positive direction. Using these velocity values over the measured time interval, we calculated acceleration 1 to be negative 0.373 meters per second squared. In a second method, using the overall change in velocity divided by the total time change of 1.350 seconds, we calculated acceleration 2 to be negative 0.096 meters per second squared. When we compare these experimental accelerations to the theoretical value of 0.700 meters per second squared, we observe a significant difference in magnitude. The experimental accelerations are smaller and negative in direction. This discrepancy suggests that the real system did not behave as an ideal system. Several factors likely contributed to this difference. First, friction between the cart and the track would reduce the net force acting on the system, thus lowering the acceleration. Second, friction within the pulley system may have absorbed some of the energy that would have otherwise contributed to the motion. Air resistance, although small, could also play a minor role. Additionally, small measurement errors in timing and position, especially when calculating velocity from small position changes, can significantly affect acceleration calculations. Even slight inconsistencies in how the masses were measured or distributed could influence results. The variation between acceleration 1 and acceleration 2 also highlights how sensitive acceleration calculations are to small errors in velocity and time. Because acceleration depends on the rate of change of a velocity, any uncertainty in those measurements is amplified. Despite these discrepancies, the overall trend in the data still supports Newton's second law. The system clearly demonstrated that acceleration depends on the applied force and the total mass of the system. While the exact numerical agreement was not perfect, the experiment successfully showed that increasing force produces acceleration, and that the real-world conditions prevent systems from achieving ideal theoretical values. In conclusion, this experiment reinforced the principles of Newton's second law, while also demonstrating the importance of accounting for experimental error and non-ideal factors in real laboratory conditions.